This is video 17 in the behavioral analysis series, and we're just continuing off from the last video, but we discussed series, and this is video 17, and we'll go into some examples. So the alternating harmonic series, that's the series where basically alternates the minus sign, so like it goes from 1, then minus 1/2, positive 1/3, to minus 1/4, and so forth. So it took the series of the format -1 to the n plus 1, and then times 1 over n. So this is an alternating series. Alternating series test says it's going to have the structure of like -1 raised to some exponent, say n plus 1, and then an. Now if an is monotone decreasing, and then an converges to 0, then this alternating series, this converges by the alternating series test. So for this question, for example, we have the series -1 n plus 1 times 1 over n, n equals 1 to infinity. Right, and if you plug 1 in, that's -1 of the 1 plus 1, it's -1 squared. That makes the negative go away, so you just get 1. N equals 2, that's going to make that an odd exponent, -1 of the 2 plus 1, that's -1 cubed, make that minus, and then 1/2, and then it just alternates signs like this. But our sequence an, in this case, is the 1 over n. We know 1 over n converges to 0. And also, this is a monotone decreasing sequence. Right, because monotone decreasing has the terms x1 greater than or equal to x2, greater than or equal to x3, and so forth. So you have xn greater than or equal to xn plus 1. That's monotone decreasing. So we know in the natural numbers is inductive. Also, n plus 1, right, is greater than n for all natural numbers n. So therefore, 1 over n plus 1 is less than 1 over n. 1 over n plus 1, that's the nth plus 1 term, and that's less than the nth term. So this is monotone decreasing. Okay, so since it's monotone decreasing, and since the sequence 1 over n converges to 0, this converges by alternating series test. Okay, so that's just an example I figure I'll start out with. That's not difficult. I did work it out right here, everything I said. Now here's another example. To prove the series 1 over n times n plus 1 converges. Further, it's possible to find sum. Now, maybe I don't remember, but partial fractions is a technique that we can write. So we can try using partial fractions. So to write, and you'll see why I do that. So to write 1 over n times n plus 1, that's equal to some value over n plus some value over n plus 1. Okay, so that's what we're going to try to do. Multiplying by the denominator n times n plus 1, that gives us 1 equal to a times n plus 1 plus b times n. Now, if we let n be 0, then you have 1 equal to a times 0 plus 1 plus b times 0. That cancels out, so you just get a is equal to 1. Now, if n is negative 1, you get 1 equal to a times negative 1 plus 1, and then b times negative 1. So that's 0, so you have negative b equal to 1. So then b is negative 1. So we can write this as, so we had a over n, a is 1, so that's 1 over n, and then b is negative 1, so the minus 1 over n plus 1. And what does this look like? So if n is 1, that's going to make this 1 minus 1 half, that's when n is 1, plus when n is 2, that's 1 half minus 1/3. I think you get the pattern, so when n is 3, that's 1/3 minus a fourth. So the nth partial sum, Sn, is this, and it's a telescoping series. The negative 1/2 cancels the positive 1/2, negative 1/3 cancels 1/3, and then so forth. And so we get to, so Sn, nth partial sum is equal to 1 minus 1 over n plus 1. So we know this will converge to 1 as n goes to infinity. So the sum of 1 over n times n plus 1 equals our the limit of the nth partial sum. We wrote it as a telescoping series, and that limit turned out to be 1. All right, so that's, so yeah, it converges, its sum is 1. All right, now prove the divergence of the harmonic series. So there's a bunch of proofs for this. All right, well, the quick answer is it's a P series. This is P series with P equal to 1. So we know it's going to diverge. Since the P series converges when P is greater than 1. All right, and that's the quick answer. Now, let's suppose we didn't know the P series. Okay, let's suppose we didn't know about P series. All right, so for sake of contradiction, assume the harmonic series does converge, and let's say it converges to some number f. All right, so we're going to prove that we'll get a contradiction. So we know f is going to equal the sum of this, and the sum of this is going to be 1 plus 1/2 plus 1/3, and then I'll write it all the way up to plus 1/8. And we could group terms like the following. So this is equal to grouping 1 plus 1/2, and grouping 1/3 plus 1/4, and then grouping 1/5 and 1/6, and then grouping 1/7, 1/8. All right, and so this sum 1 plus 1/2, this is greater than 1/2 plus 1/2. This sum 1/3 plus 1/4, that's greater than 1/4 plus 1/4. 1/5 plus 1/6 is greater than 1/6 plus 1/6. And then this is greater than 1/8 plus 1/8. So essentially all of this is going to be greater than adding these. And what is this going to give me? So that's going to be 1/2 plus 1/2 is 1. 1/4 plus 1/4 is 1/2. So all of this is equal to 1 plus 1/2. 1/6 plus 1/6 is 1/3. 1/8 plus 1/8, 2/8, 1/4. And you see that this is the same thing as s, right? So this is s. And so we got s being bigger than s contradiction. All right, so therefore it diverges. Okay, so that's one of many proofs to show that the harmonic series diverges. I like this one because I think it keeps it simple enough. Okay. Prove that the series 1 over n squared plus n converges. I'll do it down here. So all right, so note that for all n, right, n squared plus n is greater than n squared. So 1 over n squared plus n is less than 1 over n squared. And these are natural numbers, so then we have that between 0 and the series 1 over n squared, n equals 1 to infinity, that converges since it's a p series with p equal to 2. So by comparison test, the convergence of 1 over n squared implies the convergence of 1 over n squared plus n. All right, and recall that comparison test. You need it so that you have 0 less than or equal to an less than or equal to bn, and then the convergence of bn implies the convergence of an. Right, so that converges by comparison test. Now, number 5. It's 1 over n squared and then minus n plus 1. And then we're going to prove this converges. All right, and proof of 4, we compared to 1 over n squared, but note that, let's say if n is 1, right, so n squared minus n plus 1, that's equal to 1 minus 1 plus 1, which is 1. N is 2, so that's going to be 2 squared minus 2 plus 1, that's 4 minus 2 plus 1. That's 3. Now if we had n squared, when n is 1, that's 1. And then n is 2 is 4. And let's see, so for this one that we did, we had that n squared plus n was greater than n squared. So that allowed us, when you take the reciprocal, we had 1 over n squared plus n to be less than 1 over n squared. But for this, you see that comparing terms, so like for n is 2, we have 3 versus 4. And then comparing 3, we have 7 versus 9. And so we would have n squared minus n plus 1 to be less than or equal to n squared, which would mean the reciprocals would be that. And I can't use the comparison test with n squared then, because that would, I need it in the opposite reverse direction. Okay, so we can't use the comparison test in this case with that particular series 1 over n squared. But for the limit comparison test, which states that if an and bn are strictly positive, and the limit of an over bn equals L, so we have two things. If L is greater than 0, then the series an converges if and only if bn converges. And then if L is 0, then the convergence of bn implies the convergence of an. Right, so that's the limit comparison test. Now, for our question, we have 1 over n squared minus n, I believe it was plus 1. And then I'm still going to use 1 over n squared. So both of these, so like, let's say I said this was my an, let's say this is bn. If I take the limit of an over bn, that's the limit n squared minus n plus 1 over n squared, which is going to give us 1. So that's greater than 0. And we know our 1 over n squared converges by p series. By a p series with p equal to 2. So by limit comparison test, this is if and only if our series 1 over n squared minus n plus 1 converges. All right, so that's that answer for that one. So for number 6, this will be our last example for this. If the series AN with the sequence of AN being positive greater than 0 is convergent, is the series of AN squared always convergent? Either prove it or give a counterexample. And it is, in a strict requirement, is we needed this we need that assumption. So why? Let's consider alternating series -1 to the n and over the square root of n. And that's n equals 1 to infinity. This will converge by alternating series test because our an is 1 over square root of n, which is 1 over n to the 1/2. And for p series, right, it should converge. Make sure I have that right. Hold on. All right, sorry. That's it doesn't converge by because that's a p series. Because right, p is 1/2 in this case, and so 1 over the square root of n actually diverges. All right, so ignore this, but this still does converge, and we still have the terms that are not necessarily positive. So, but this converges by alternating series test, though. All right, and what do we need for alternating series test? So our AN is 1 over square root of n, or 1 over n to the 1/2. And as far as alternating series test, we need monotone decreasing sequence. And we need that AN converges to 0. Well, this definitely 1 over square root of n converges to 0. And it's monotone decreasing. Right, since we're all n, we have that the square root of n plus 1 is greater than square root of n. So 1 over square root of n plus 1 is less than 1 over square root of n. And so we have the n plus 1 term is less than the nth term. Right, so that's monotone decreasing. All right, so this converges by alternating series test. The terms an are not greater than 0. Further, when we do the series with it squaring the terms, so that does convert by alternating series test when we square it terms. What is that going to give? So that's going to give us -1 to the 2n. Squaring a square root cancels out the square root, so you just have n. 2n's an even number, so -1 raised to an even number is just 1. That's really the harmonic series which diverges. Okay, so this is the case where AN converges, but squaring the terms AN squared diverges. And in this case, we had the terms AN not be greater than 0, so we're alternating from negative to positive. Okay, so that's the case where it does not have this requirement of the terms AN greater than 0. And so when you do have that assumption, I claim that the AN squared series does converge. So claim converges, then AN squared converges. Okay, so there's more than one way to do this. I'll show two proofs. So this will be proof one. So since AN converges, then the limit of AN is 0. Okay, so this means for all epsilon greater than 0, there exists some capital N, so that for all little n bigger than capital N, we have the absolute value of AN minus 0 to be less than epsilon. So that's true for all epsilon. Pick epsilon to be 1. So then we have the absolute value of AN less than 1. Well, that means our terms, so AN's positive, so AN is less than 1. And so it's between 0 and 1. Since AN is greater than 0. Well, for AN squared, if we're restricting ourselves to be between 0 and 1, that's going to be less than, I guess you'd say less than or equal to AN less than 1. That's for all n bigger than n, in which the absolute value of AN less than 1. Okay, so since that's the case, we know this converges. So by comparison test, the series AN squared converges for all n bigger than capital N, where n is this cutoff value. That's a natural number. So that converges for all indices little n bigger than capital N. And that's an infinite amount of terms. Now, since there are finitely many terms before this, A1, A2, dot, 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 AN, that sum is finite. So I should probably say AN 1 squared, a1 squared, a capital N squared. The sum of, let's say, a n squared from n equals 1 to capital N is finite. All right, so keep the series from n equals 1 to infinity of a n squared equals from n equals 1 to capital N of a n squared plus from n equals n plus 1 to infinity of a n squared. So this is finite. That converges because we used the comparison test with an. So because of comparison test from above, so this is finite then. So the whole thing converges. All right, so that again, so what we did for this was use the fact that the series an converges. That means the sequence of an is 0. So since that's the case, that means for all epsilon, there exists a capital N such that for all little n bigger than capital N, the distance between the terms of an and 0 is less than epsilon. So since that's for all epsilon, I just chose epsilon to be 1. So then we have that the absolute value of the terms an to be less than 1. Well, we know the terms are positive, so we can say that we have zeros less than an less than 1. Since the terms are between 0 and 1, then we're dealing with fractions, and so an squared is going to be less than or equal to an less than 1, right? Because for n bigger than 1, an squared is bigger than or equal to an. So for n less than 1, right? So we're going to have it such that the n squares are less than or equal to an. Okay, so when we think of it as whole numbers bigger than 1, yeah, the squares are going to be bigger, but since they were between 0 and 1, the squares are going to be smaller. So that's why we have 0 less than an squared less than, or we could say is less than or equal to an, which is less than 1 for all indices little n bigger than capital N. All right, so, and that's in which, again, so for the absolute value of an to be less than 1. So we know this series an converges. So by comparison test, the series of an squared converges, and that's true for all little n bigger than capital N. So now there are finitely many terms that come before this particular, for all the indices that come after capital N. And since there's a finite amount of terms, then the sum of the an squares from n equals 1 to capital N is finite. So for the series itself of an squared from n equals 1 to infinity, that is the same as taking the sum of n equals 1 to capital N plus n equals capital N plus 1 to infinity. And we know the first thing converges because that's a finite sum. And the second thing converges because we just stated so by the comparison test. So therefore the series an squared converges. All right, so that's the proof 1. Proof 2. Okay, so this converges, and we know all the terms an are greater than 0. So Sn, the impartial sum, which is a1 plus a2 plus a3 dot dot plus an. We know the sequence of impartial sums converges. It converges to S. Then squaring the limit. So since limit n equals infinity of Sn equals S, then the limit, squaring the limit is equal to S squared. Nice. So we know that's the case for the Sn's, where the Sn's come from the partial sums of partial sums of this from the series of an. Right, so we know that. Now for the series of an squared, I'll let Tn be the partial sums of that. So that's going to be equal to a1 squared plus a2 squared plus a3 squared dot 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 plus an squared. Okay, so we know that. And what can we say? So I claim, so first notice that this is the sequence of n partial sums Tn is monotone increasing, right? Because for all n, we know T1, a1 squared, T2, a1 squared plus a2 squared, which is greater than T1, a1 squared. So then dot 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 Tn a1 squared, or sorry, the n plus 1, T of n plus 1. That's greater than Tn, right? That's a1 squared all the way up to an squared. So for all n, we have that Tn, the nth term is less than or equal to the n plus 1 term, or really less than. So it's monotone increasing. So it's a monotone increasing sequence. So we know from the monotone convergence theorem says if you have a monotone sequence, and then the sequence an, let's say it's monotone, that converges if and only if it's bounded. Okay, so Tn is monotone. And so I need to show that it's bounded in order to say it converges. Okay, so that's what the logic is that I'm using in this. So Tn is the sequence of n partial sums of the series of an squared. It's a monotone increasing sequence. And so I know, since I know it's monotone, if I can show it's bounded, then it converges by the monotone convergence theorem. And if I'm going to show it's bounded, I'm going to make use of what we know for the series of an converges. So we know when we square it, we get limit of Sn squared, which is S squared. Now, when you do Sn times Sn, what does that come out to be? So you can do a1 times all the terms in the other one, so that's a1 squared plus a1 times a2 plus a1 times a3 plus a1 times a4 dot 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 plus a1 times an, and that's greater than um, a1 squared. So then when you do, so then plus, now if I multiply a2 by all the other terms, that's a1 times a2, so a2 times a1 plus a2 squared plus a2, a3, a2, a4, and then dot 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 plus a2 times an. And that's greater than, right, a2 squared. You can keep going like this. You multiply it all the way through. So when you distribute the an, you get an times a1, an times a2, an times a3, an times a4, plus an squared. That whole thing, that's greater than an squared. And so what we've shown here, so that all of the terms from Tn, all of those is less than Sn squared. And so for all n, and so the sequence Tn is going to be less than S squared, since that's the limit for the Sn squares. So therefore, it's bounded. It's bounded above by S squared. Bounded above by S squared. Hence, since Tn is monotone and bounded, it converges by monotone convergence theorem. So since the sequence of impartial sums converges, that means the series A, that since our Tn consisted of the sequence of a n squared, where you're taking the sum of those, then the series of a n squared converges. All right, so that was the second proof was the way I did it at first. Um, I just looked at, well, what are the terms of the sequence of impartial sums for a n squared series, and noticed that, well, that's bounded and it's increasing. So by monotone convergence theorem, it's going to converge. Right, so it's bounded above by uh, each partial sum of Tn is bounded above by the nth partial sum squared, and is the limit of the from the sequence an. And so when you take the limit of Sn, that becomes S squared. So our limit for the sequence of the Tn, everything's going to be bounded above by S squared. All right, so that's it for this video. Next video, we're going to start something else.